This webcast talks about motion maps and shows some videos of things moving, and then we'll create the corresponding motion maps. So first, let me go to the video, and I'm going to show a bowling ball moving across a gym floor. Let's watch it before we talk about it. So we're seeing the bowling ball moving along the gym floor to the left. The gym floor has floor tiles that are 1 foot on each side. So we can count the number of tiles and use that to get an idea of how far the ball is moving. And you're hearing someone yelling 1, 1, 1. They're acting like a metronome. Every second they're calling out 1, and that way the woman in the blue shirt, she knows that when she hears the 1, she should drop a packet on the floor to mark the position of the bowling ball at that point. So what we're seeing is these packets are identifying the position of the bowling ball every second. In other words, those packets are identifying the position at even time increments, right? As every second passes, we get another packet that shows the location of the bowling ball at that time. It seems to me that these packets are evenly spaced. So as each, and I can count the floor tiles to try to see how far the ball has gone in each second. And here I see 1, 2, 3. I'm just going to call that 3. Every second, the bowling ball is moving about 3 feet. So let's go make a corresponding motion map that matches this situation. Okay, so the first thing that I need to do to make a motion map is to draw an axis and to put a scale on it. Now the axis is showing location or position, not time. It's showing position. And in this situation, the bowling ball was moving to the left, so I chose to number my scale, going from 0 on the right-hand side to larger positions on the left. I think that would work. And okay, so to do a motion map, I'm going to put position dots, small dots that indicate the position of the bowling ball every second. Now, I'm going to say that at time 0, the bowling ball was at position 0. And so I will put my first dot at the 0 position. Then, after a second had passed, the lady put down a packet and it was about 3 feet away. So my next position dot is at the 3 foot mark. And then after another second passes, the bowling ball was at the 6 foot mark. And after another, it's at the 9 foot. Okay, so the bowling ball is moving about the same distance every second, and the little packets that the lady was putting on the floor are similar to these position dots that I'm putting on my motion map. After I've put the position dots, then I want to go back and draw velocity vectors. The velocity vectors are arrows. The arrow should point in the direction of motion. So in this motion map, the arrows are pointing left because that's the direction that we saw the bowling ball move. And the arrows start on the previous position dot, and they come almost to the next position dot. It's important to leave this small gap because we don't want the arrow, which is showing us direction, to be covered up by the position dot. So leave just a little space there between them. So I'm seeing that my velocity vectors, these arrows, are all the same length. That means that the bowling ball was moving at a constant speed. the speed is not changing as the seconds go by. Let's go look at another example of the bowling ball moving. Now we'll watch the bowling ball moving at a faster speed. Okay, so the lady in the blue shirt, she had to scramble a little bit because the ball is really moving much faster across the gym floor. So she's dropped the packets every second, the same way that she did before, but now those packets are spaced further apart. Because it's moving faster, the bowling ball is able to go a greater distance in the space of each second. And I can kind of count the floor tiles. Here's 1, 2, 3, 4. These packets are spaced about 4.5 feet apart. So that's about how far the bowling ball is moving every second. Let's go and create a motion map for this type of motion where the bowling ball is moving a little faster. Okay, so I set up another axis and put a scale on it, similar to the way I started for the previous motion map. And again, I'm going to say that the bowling ball is starting at position 0 meters. Okay, but now after 1 second, the bowling ball has moved further. It has moved 4.5 feet. And when another second passes, it's gone another 4.5 feet. And then another second, it goes another 4.5 feet. So look, my position dots are spaced further apart on the motion map, just like the packets on the floor were spaced further apart. So if you can compare to the previous motion map, I'm still showing 3 seconds worth of data, right? We started at time 0. Here's where it is at 1 second. Here's where it is at 2 seconds. Here's where it is at 3 seconds. So I'm doing the same thing for this faster bowling ball. Here it is at 0. Here it is at time 1 second. Here it is at time 2 second, time 3 second. But it has gone much further. The position dots are spaced much further apart. I'll draw in the velocity vectors now, and the arrows, the velocity vectors, are also longer in length. That longer arrow indicates a faster speed. They are all the same length because the bowling ball was moving at a constant speed, but they are longer than in the previous map because it was moving faster. So in the first case that we looked at, the bowling ball was moving at a constant speed of 3 feet per second, and that's indicated by our arrows or velocity vectors all being the same length. In the second example, the bowling ball was moving at a faster constant speed of 4.5 feet per second, indicated by these longer arrows all being the same length. Now let's look at what happens if we roll the bowling ball across a piece of carpet. So now the bowling ball seems to be slowing down. If I look at how far it's moving between when the packets are placed down, the packets are getting closer and closer together. These packets are closer than these, and these packets are closer than these. So the distance between the packets is gradually getting smaller because the ball is slowing down. There's friction between the bowling ball and the carpet that causes it to slow. Let's make a motion map for this scenario. Okay, so I have set up my axis and put a scale on it to show the motion map of the bowling ball on a piece of carpet. At time 0, the bowling ball is at position 0. So the first position dot goes where it started, at position 0 feet. After the first second, it has moved fairly far, about 4 feet. But in the next second, it only moves 3 feet. So it has moved a little less far in that second. In the third second, it only moved 2 feet. So see, the position dots are getting closer and closer together. In the fourth second, it only moved 1 foot. So they're getting much closer. So now I'm going to put in the velocity vectors. These vectors all point to the left because that's the direction that the ball was moving. But you can see that the arrows are getting shorter and shorter. That's because the ball was slowing down. And so slowing down on a motion map is indicated by arrows that become shorter. Let's look at one final example of this bowling ball, and now we're going to have someone who pushes the ball across the floor with a board. Okay, so let's watch that. So in this situation, the packets got further and further apart. The man is pushing the ball with a board, and he's making it go faster and faster. Let's create a motion map for that situation. Okay, so here we've set up an axis with a scale to show the position of this bowling ball that's being pushed by a board. The first position of the bowling ball is at 0 feet. And when he first starts to push it, because at the beginning it was not moving, when he first starts to push it, it doesn't go very far in the first second, but in the next second it went further, and then in the next second it went even further, and then a lot further in the last second. So it is speeding up. As each successive second passes, the ball is moving further and further. And if I put in the velocity vectors, we see that the arrows all point to the left because that's the direction the ball was moving, but the arrows are getting longer to indicate that the ball was speeding up. So when you have a situation where something is speeding up, you can see that because the arrows become longer.